Moving on for our experts talk. Next, we have a presentation from the team of Dr. Sandra Gelbridge. She's an assistant professor in the Department of Mechanical Engineering at the Chemnitz University of Technology in Germany. Her research interests are on utilizing resources towards carbon neutrality in the area of 3D printing of concrete structures. Unfortunately, due to time differences, she won't be able to join live, but we have a recorded talk from her and her team. So we will be playing the recorded talk.
To our presentation, in which we would like to present the work of our research area, lightweight construction and civil engineering in the field of additive manufacturing of concrete. First of all, I would like to start with a short introduction about our motivation, who we are and what we do. I will then give you an insight into our concrete printing working environment and the way we generate our geometries and plan the production for the concrete printing. And finally, I will shortly present some completed and ongoing projects. Let's start with a short introduction. Lightweight structures are important and the key technologies of the future. On this table, you can see a picture of the extraction of resources in the world, and overall resource extraction has steadily increased over the past 30 years. So the building industry is responsible for more than 50% of energy and non-energy resource extraction, and that's very much. So the aim is to reduce the consumption of resources, and this aim requires the implementation of lightweight constructions in civil engineering. So our motivation for lightweight in civil engineering is to save material, weight, and ecological resources. In this table, you can see the core competencies of our research group. First is the material lightweight design, and we develop lightweight and powerful polymer and concrete-based composites with fiber and textile integration, resource-efficient manufacturing technologies, and testing methods of material and construction units. The second part is structural lightweight design. That means lightweight design, calculation, and optimization. So here we generate elements and lightweight constructions, and that means structural lightweight design, mobile lightweight architecture, joining technologies, design and calculation, as well as acoustic optimization. The third method is the integration of functions for monitoring, insulation, and illumination. So we develop textile reinforced hybrid structures with functionalization. One of the most important future technologies for the construction is the 3D printing of concrete structures. In our research group, we have been developing this technology for the last 4 years. We are focused on the application of 3D printing for the efficient production of precast elements, and we combine this technology with wet casting technology and concrete spraying. Now we come to our research field of automation in civil engineering. In our lab building, we have our robot arena, which consists of 2 KUKA robots. The first one is currently used exclusively for the concrete extrusion, and the second one can be used for milling, fiber laying, and handling. Our workspace has a length and width of 1.5 meter and a height of 1 meter. And the concrete conveying system we use is the PFT Bolero mixing pump, which consists of a screw housing, a screw conveyor, and a container. And here you can see our robot arena in reality. For the production planning, we use Grasshopper, which is an add-on for Rhino, and KUKA PRC, which is an add-on for Grasshopper. Here you can see the structure of such a Grasshopper file. And with Grasshopper, we create or prepare our geometries, and the geometries can be built up parametrically. We also do the slicing of these geometries and the path planning with Grasshopper, and based on this, we generate the final robot commands with KUKA PRC. In this video, you will get a short demonstration of what parametric design with Grasshopper means. So you can change, for example, the basic dimensions, the curvature, the number of honeycombs, as well as the layer dimensions. In this video, you will get a short demonstration how to get to the robot program and how to simulate the robot movements with KUKA PRC. Therefore, the lines and curves are divided and planes created in the resulting points. Based on these planes, the motion commands for the robots are generated, and it's also possible to display the required printing time and the amount of material. And now I will give you a short impression of our work. One completed project was about the development of a highly loadable material composite by integrating uncured fiber-reinforced plastic composites into processable fresh concretes for the efficient production of thin-walled precast concrete elements. This project was the starting point for us to get into the 3D printing of concrete. And one goal here was to increase the bond strength between fiber and concrete using a special process. And in addition to the mechanical bond, we created an additional material bond here. Here you can see the process of the fiber integration. For this purpose, a special fiber laying unit with integrated fiber spreading and impregnation, as well as an extrusion unit for the concrete were developed. Here you can see a short video sequence of the whole process consisting of the fiber integration and the concrete extrusion. One current project is about the 3D printing and milling of complex concrete elements for the production of casting resin molds. The primary focus is on prototype construction as well as small and medium-sized series. Due to the high cost share of the individually shaped molds, the motivation is to produce high-quality concrete elements with complex geometries as precast elements, and the recyclable formwork system will enable resource saving and thus an environmentally friendly production of precast concrete elements. Therefore, a material with a very small maximum grain size was developed, and the developed concrete can be printed close to the final contour and then milled to the exact contour when cured. And in the final step, the model can be molded with a suitable casting resin. Here you can see a short video sequence which shows the steps as mentioned. For the validation, a test specimen with a pyramid structure corresponding to a practice-relevant geometry was implemented, and the resulting casting resin mold was tested with different concretes. Here you can see a practical application of the research partner. It's a curbstone with a defined surface texture. We printed the curbstone as a shell body to reduce cost, time, and mass, and we filled it with a gravel and other materials to ensure the stability of the structure and print the final top layer. Here you can see a time-lapse video of the printing of the curbstone. In the remaining project period, the milling of different structures, the implementation of molds with different resins, and the recycling and reuse in the material cycle will be performed. Another current project is about the continuous production of thin-walled fiber-reinforced precision concrete elements for modular freeform constructions. The motivation here is to combine the production technologies concrete spraying and concrete extrusion, and in addition, the automated integration of mechanical anchors in the correct position and an automated quality control are being investigated and integrated into the process chain. The first step in the process chain is the robot-based spraying of the concrete in a formwork, and the second step is the extrusion of a rib structure which serves to support the thin concrete shell. The research focus here is on the development of a recipe for both processes, the programming of the robot, the surface quality, and the development of a multi-purpose nozzle for concrete spraying and extrusion. The next step in the process chain is the integration of the anchors into the rib structure. For this purpose, different variants of anchors were developed and tested. And in addition, a special handling system for the integration is being developed. The research focus here is on the analysis and evaluation of the bond behavior and the integration technologies. The integration of the anchors is followed by the quality control. For the measurement of large-scale concrete elements, different methods are investigated and evaluated, and the research focus here is on large concrete elements as well as fast data acquisition and evaluation. The final step is the clearing of the work area. The requirement here is to clear the work area as quickly as possible to reduce the cycle time. And the research focus here is on the required waiting time until further transport, as well as the component stability at maximum acceleration. The next project with the title Efficient Inline Production for Mineral Manufacturing Processes deals with the combination of the concrete casting and extrusion. The goal here is to develop a stable and economical manufacturing process. At the same time, free shaping without additional formwork should be possible, and as a result, a prototype plant is to be realized at the project partner. Here you can see the working steps, starting with the casting of the top layer, followed by the integration of the textile and the casting of the bottom layer. Then the base is extruded, and after the curing process, the component can be stripped. The thickness of the plate is 20 mm and the height of the table 400 mm, with a layer height of 10 mm and a layer width of 20 mm. And the extrusion velocity used here was about 60 mm per second. On this slide, you can see two time-lapse videos showing the extrusion of two different variants of the table base. The production time for each of these is about 10 minutes. Thank you for your attention. For further information, please contact Professor Gelbridge.
I would like to thank Professor Sandra Gelbridge and her team for sending us the recorded talk. I am sure the audience must have greatly benefited from her expertise. Moving on, our next speaker is Dr. Fallacy, who is an assistant professor in the departments of Mechanical and Industrial Engineering and Civil and Mineral Engineering at the University of Toronto. Her main areas of research are sensor development and assessing the performance of novel sensing devices and developing decision-making frameworks. So I hand it over to Dr. Fallacy.
Hello, everyone. Can you hear me and see the presentation?
Yes.
Okay, great. So it's a real pleasure joining this workshop with you. So thank you so much for having me in this workshop. I am an assistant professor at the University of Toronto, and I'm jointly appointed between the Mechanical and Industrial Engineering Department and the Civil and Mineral Engineering Department. So in this very short presentation, I'm going to try and give you an overview of my general research area and then highlight some projects. But as you'll see, unfortunately, I haven't gotten to do much research on 3D printed concrete, but I will try to draw some parallels between the research that we have done in my group and the research that's being done in 3D printed concrete, and hopefully extensions of some of the work that we've done to contribute to smart 3D printed homes, smart and functional, in fact. So my general research area is structural health monitoring, and that means that we instrument various engineering structures. They could be buildings, bridges, planes, whatever engineering structure or system that you have, and then we use the data from those sensors to extract information that would help us make timely decisions about the performance or the maintenance of that structure. Now, the two main components of research in structural health monitoring is sensors and then making decisions based on the data that we get from those sensors. So the data is kind of the common denominator there. And my research tries to focus on some of these aspects. Now, in terms of sensors, we usually work on developing our own sensors and sensing materials, but sometimes we use commercially available sensors for specific applications or adapt them to specific applications. And those applications have generally so far been on bridges and wind turbines and prosthetic devices, but they kind of evolve over time. So just a brief overview of some of the sensor development that we've done. A major part of that has been working on smart or self-sensing materials, and in particular piezo-resistive materials, which means materials whose electrical resistance changes in response to stress and strain. And so we've been working on various both polymeric and cementitious smart materials. So these composites are usually conductive. So we have a cementitious or a polymeric matrix that is reinforced with some sort of a conductive filler that could be carbon fibers or steel fibers or carbon nanomaterials. So we have done quite a bit of work on self-sensing cementitious composites that could be integrated within the host concrete structure. And like many others, we've proven the concept, but there's still a long, long ways for these materials to be used in the field, whether it's for a smart concrete structure or for as components to be added to various structures like a bridge deck for traffic monitoring or for way in motion. And so we've also looked at developing cementitious sensors that are not discrete, rather as a sensing skin, so that the whole concrete structure can be a sensing or a sensate material where you can detect cracks and damage and everything in spatially rather than discretely. So then that work has also been extended or worked on in parallel with silicone material as the matrix as opposed to concrete. And these sensors would then be used more in biomechanical applications. And so very similar concepts, just different kind of materials. In addition to smart materials, we've also partly focused on developing fiber optic sensors in-house and also using commercially available fiber optics. And that's mostly been because the functionality and the flexibility and the fact that we could multiplex these fiber optic sensors have been very attractive for the kind of applications that we've looked at. And one of the things that we've really liked about fiber optics is their small size, which helps this kind of application to be very, very unintrusive to the whole host structure. And so one of our inspirations has been developing vibration sensors using fiber optics, kind of inspired by how in nature, for example, the antenna of a bee has receptors that can sense various signals, including vibration. So we set about to develop a fiber optic vibration sensors. Now these are available, but they still use mass spring parts, the commercially available ones, which makes the product a little bit bulky and non-durable. So part of our work focuses on developing fiber-only accelerometers. Now, while we do develop sensors, sometimes we're concerned about how do we integrate these sensors into structures. And while I said we haven't worked on 3D printed concrete, we have worked quite a bit on traditional 3D printed components. And again, as I said, the impetus was that the 3D printed structures gives us the flexibility to integrate sensors within the structure. And so one of the things that we found is when we switch from traditional manufacturing to 3D printed manufacturing for any engineering structure, we need to be able to characterize that material to make sure that it's strong enough and durable enough and flexible enough to be used for that application. So a large part of our work has focused on performing material testing on various 3D printed components and looking at their failure mechanisms and their various material properties. Because I have an appointment in the mechanical and industrial engineering department, I have students in industrial engineering who would be able to work mostly on the data that we get from sensors. So I've been lucky enough to have a few students who have dealt mostly with the data, and some of that has focused on developing condition-based maintenance methods. And what we do there is we look at a smart ecosystem, like a smart city, and we take we focus on a specific structure, for example, a bridge, and then a component within that structure, for example, a bridge deck. And we look at the data that we get from either sensors or from inspection data over time, and combine that with either optimization or AI techniques to come up with dynamic decision making. And our focus has mostly been on keeping the decision-making framework very, very simple so that it can actually be used in the industry. So typically what we do is we transform these decision-making frameworks into very simple control chart type project type frameworks. For example, the one that you see below, on the vertical axis, you have hazard levels, and on the horizontal axis, you have time periods. And so you could decide then very easily based on these charts whether to do no action or how much maintenance you actually require at every given point. Another kind of data related project that we've worked on is in collaboration with a company that uses various sensors to monitor monitor the water quality in swimming pools, and then manage how much fresh water we would add to the swimming pool. So we've been working on the data provided by that company to be able to make decision frameworks based on that. Now, so as I said, I'm going to just draw some parallels between our research and what's being done in additive manufacturing. And the first one is has to do with testing and characterizing these materials. So as you all know, as engineers, we always tend to first, whenever we want to design a new material, we go to various standards and we test the material, characterize it based on these official standards, and then have the ability to say, okay, this material is good for this function. But it turns out that for 3D printed, even for the conventional 3D printed materials, there's no real available standard. And what people have been doing, they've been using available standards for fiber reinforced polymers, for example, and then slightly adapting that. So our contribution to that has been to look at various testing methods. So again, I don't need to belabor the benefits and the flexibility that we get with 3D printed homes. And I just looking at some of these publications, it seems that a large number of people are looking at 3D printed concrete, and there's been so many very interesting research going on. Some of them already mentioned in this workshop, and one that I found quite interesting also was a research group in Australia looking at the stacking sequence that was inspired by a lobster shell. So we have not worked on concrete structures or 3D printed concrete structures, but I think that the work that we've done in contributing to developing new testing methods or developing the actual specimen that would be tested for material characterization could have parallels with the type of research that's being done in testing 3D printed concrete. And I was very pleasantly surprised to see that there's a lot of research going into that, looking at the interlayer bond, looking at the moisture and the bond strength and various different tests. So that's one parallel that I can see. Another parallel that I can see, especially in sensing, is that a lot of people have tried using fibers, and specifically steel fibers, to strengthen the bond strength of the 3D printed concrete. And if you remember our cementitious sensors, where we use cement plus carbon fiber, this is just a microscopic image of it. And on the right, you can see an image of a 3D printed piece of concrete that has steel fibers in there. So I imagine that because steel fibers are conductive, that material could potentially also be a 3D printed cementitious sensor. Now, just to combine all of these different avenues of research that's traditionally done for smart structures, they could all be very well combined using similar concepts and adapted to have smart and functional 3D printed homes, which I think will be a major field of research that will be ongoing and hopefully in the future. So with that, I'd like to thank everyone. And if you have any questions, please let me know. I am in a different time zone, so I'll have to step out for a little bit, but I'll try to rejoin again in a couple hours when I get home. Thank you.
Okay, sure. So thank you, Dr. Azari. Hopefully you can join us for the panel discussion.
Thank you.
Moving on to our next and last speaker is Dr. Yami Zhang, who is a professor at the Southeast University in Nanjing in China. She also serves as the director of the Nanjing Institute of Intelligent Additive Manufacturing in China. Her expertise lies in the area of high-performance 3D printed concrete, geopolymer composites, and the reuse of solid waste in concrete. With this, I invite Professor Zhang for her presentation.
Okay, great. Thank you. First, I would like to thank Professor Lim Benzia for giving me this chance to talk at the workshop. I will talk about 3D printing concrete and some recent development in China. I think this topic is also well in agreement with the workshop theme about low carbon. Okay. Here are some contents about my talk. First is a very brief look at the 3D printing concrete and its advantage. As we all know that for traditional construction, formwork is necessary, but after concrete is cast, we need to remove the formwork. So it's in fact a waste of materials and also a waste of labors. And because conventional construction is also a kind of work of need lots of labor. So it's a labor intensive work with many risk safety problem. And also in many countries, of course, including China now, we are in a lack of laborers because, we can find less and less laborers for construction. So we have the challenge for the traditional construction. So the solution is to use 3D printing concrete technology to replace the traditional concrete cast technology. There are many advantages for this new technology. For example, no formwork, and it's very flexible in design. This is very good for architectures. And it's of course, labor saving and material saving, especially the saving of the formwork material. And it can ensure safe construction. And it can provide a much higher construction efficiency. And the total cost is, of course, lower. And what's important for this new technology is I should say this is a low carbon footprint new technology. Okay, using this technology, we can have many innovative design for buildings. For example, one here. I am showing here, traditional, maybe we need to have this large area panel, but in fact, not all the part of the panels will have load bearing, okay? So in this case, we can just print the space, which is load carrying part with 3D printing technology. Also, we can use this technology to facilitate the integration of some multifunction in building elements. For example, here, we can design some spatial surface to reflect sunlight. And also for the elements, we can design some spatial elements like this one with a hollow space. We can have some heat insulation material inside to yeah, to have energy saving purpose for the building. Okay. In fact, there are already many attempts to use 3D printing concrete technology to build our buildings like this I show here. But I will not talk about this. I mainly focus on the research in my lab and the use in China, the use of this technology in China. In fact, currently for 3D printing concrete technology, the most widely used material is mortar. This is concrete without any aggregate. That means for concrete, for the mortar, in 1 cubic meter of mortar, more and more cement will be used to for printing. Okay, that means, you know, more cement used means very high low carbon footprint for this special material. And another issue is the cracking problem with mortar, because there is no coarse aggregate to restrict the shrinkage of mortar like conventional concrete, which use many coarse aggregates. So you can see some cracking of the printed elements after exposure in the air for a long time. So this is a problem for the current technology. One issue is it's not low carbon. Another one is a cracking problem. So in our lab, we have developed some technology to print with concrete with some coarse aggregates. Here you can see we can smoothly print the concrete with coarse aggregate, and you can see the interface problem. There is no interface problem for this concrete. That means we can increase the low carbon and also increase the property, especially the cracking resistance of the concrete. Okay, another solution for low carbon of 3D printing concrete is to use some other binding material to substitute ordinary Portland cement, which is a high energy consumption and a very high CO2 emission. This material maybe we can use alkali activated material like alkali activated slag, and we can even use some industrial waste like steel slag and ferronickel slag, and even some waste from demolished construction buildings. Yes. So this can make our 3D printing concrete more sustainable, more green. Okay. Next, I will briefly introduce some application of the 3D printing technology in China. Here I show you some these are 3 buildings in this built in Nanjing, the city where I am. And this is a sports center. This building served for the in the sports center. Okay, you can see the wall is 3D printed. Of course, 3D printed elements then assembled in situ. Okay, this building is first designed like this one here with some vegetation on the wall. This is a unique unit, a model of the 3D printed element. You can see here, we can put some soil inside and then have vegetation here. The purpose is energy saving of this building. And here we can compare 2 buildings. One is this one with living wall system with 3D printed technology. Another one is a very traditional one with aerated concrete block, and the thickness is 200 millimeter for this one, but for the left side one, the thickness is 150 millimeter. Okay, and we can compare the temperature distribution in summer. Sorry, in summer it's very hot in Nanjing. Here we show the temperature distribution of the west wall. Means the west wall with the most sunlight in summer. So we can see for this spatial wall system, the temperature is very lower, but for this one, the baseline building, you can see the surface temperature is much higher in summer. So we can see we can use 3D printing concrete technology to spatially design some energy saving buildings. Okay. Another case I want to show here is a reception center built also in Nanjing. This is a civic square in Nanjing. It's called a reception center. You can see the wall was assembled with 3D printed elements. Okay, only this small building here. Okay, here are some information about this building. It's not very large, but the area is about 280 something square meter, and the total height of the building is 5.15 meter. Okay, and totally about 96 3D printed concrete elements were assembled as the wall of the building. And for this building, we used reinforced beams and columns, but it's cast after assembling of the walls. Okay, it's cast on site. And the concrete strength is about 40 megapascal. And the service life for this building is about 50 years. And this building is designed according to Chinese standard. That means it can meet the energy saving requirement for the building, for a green building. Okay, here are some details of the design of the structure here. Yeah, you can see vertically, we can see 5 levels here, and each level is assembled with 3D printed elements. Here we can see some more details here. In fact, inside we can put some special lightweight material to enhance the energy saving property of this wall. Okay, here are some details during the production of these 3D printed elements. Yeah, we use steel reinforcement, and then we print the first layer. This is just a printed element here. You can see at both ends, we have some steels which will be connected with the neighboring elements. And also this steel can be connected with the post-cast reinforced concrete columns. Inside, we also have some EPS panel inside for heat insulation. And here is the construction of the building. The ground beam is reinforced concrete cast on site. And then we assemble the 3D printed elements layer by layer. Okay, this is the inside. This is the inside view before the column cast. Because here we can see some columns with reinforcement. Then we can cast concrete. Okay, then the whole building, the wall will be connected. Okay, and here, yeah, yes. So this is a finished building of this case. Here you can see this is a very beautiful building here. And we also have some other applications like the bus station, very beautiful. And the farm shed in Zhejiang, in a city in Zhejiang. And some public washing rooms application, also coffee house and a reception house. We have already many such kind of application using 3D printed elements. Okay. Also, we can use the 3D printing technology to print some spatial things like the animals here for the landscape in the city. This should definitely make our city more beautiful. I think many kids like these animals, like this one. And also we have printed the academic shelter, yeah, and the riverbank also some very beautiful seat in parks. Yes, I mean, we can see, so 3D printing technology can make our life a little bit different, even more beautiful, okay? And then next, I will briefly introduce some technologies in China. I mean, 3D printed concrete technology in China. This one is developed by a Chinese company called Huashan Tender. You can see here, for this one, the node is special. It's a forked nodle with the steel bars, steel reinforced inside, and then cast concrete. This is a building finished, okay? And this is a bridge in Hebei University of Technology developed by Professor Guowei Ma's group 2 years ago. This is also assembled bridge. The main elements was printed in the lab, then assembled on site. Okay, this is another 3D printed building, 2-story building. It's printed on site. You can see here, but for the columns and the beams, it's cast. Its concrete is cast. Okay, the total time for the printing is very short. It's around it's less than 50 hours, but the total project takes about 4 months because of the casting of concrete, and the roofs. This work takes a long time. Okay, and this is a very newly finished project, designed and finished by Professor Wei Guoxu's team from Tsinghua University. This is for this project, they used 3 dropped printers. They were installed on a lifting platform like this one here. And so after this, I introduced some 3D printed buildings in China. Okay.
Thank you, Dr. Zhang, for the presentation, and we will have the panel discussion just in a while. Our next speaker is Mr. Raju Goteti. He's the Vice President of Tata Consultancy Services and head of the Co-Innovation Network and a core member of the TCS Research and Innovation leadership team. So the Co-Innovation Network is a network where universities and startups can collaborate and constantly explore opportunities to create a new value with TCS. Over the last 10 years, this co-innovation network has grown to about 100+ academic partners and about 2,000+ startups globally. So I will hand it over to Mr. Raju for his presentation.
Thank you. Let me just share my screen. Can you just confirm if it is visible, please?
Yeah.
Okay. All right. So good afternoon, everyone. I'm dialing in from Toronto, and I'm going to be speaking on this topic, which is education, technology, and social impact. Just as an introduction, I lead the Co-Innovation Network for Tata Consultancy Services. This is a network which consists of academia, emerging technologies, and a larger ecosystems around the world. And IC Impacts is our COIN partner. Very proud to have IC Impacts as a COIN partner. And we have got many of the universities in the world. I'll name a few just so that you have an idea. In Canada, it's University of Toronto, UBC, McGill. In the US, it is CMU, Cornell Tech, and so on. In the UK, we have the Royal College of Arts. In Israel, we've got Tel Aviv University, University of Tokyo, many Australian universities, and most of the IITs in India. And that's a good, intersection point between IC Impacts and the TCS COIN ecosystem. It's a combination of networks and networks, which makes it really powerful. So today, I would like to talk about the technology futures of which this 3D printing is part of it. And, in what way does this shape the future? And how do we want to conceptualize this kind of, innovation and policies? And one should be doing it by design and not as an afterthought. And we do this very systematically in TCS, and what I call it as the co-innovation factors. Who are the stakeholders and how do we collaborate in order to achieve not just the technological innovation, and the roots for that, but also the way it can be implemented from an economic perspective, from a social perspective, and I'm also bringing in an education perspective on this talk today. So let me take to some real animals, going from Yame's slide to real animals. This is a construct, or a photograph of a place in Finland, in the northeastern Finland. It's a reindeer district, Savitijärvi, and 1958. And here, I would like to share what was the scenario in 1958, what happened in 1962, and what happened in 10 years from then on. This is a beautiful place, some 350 odd people. It's a territory with vast areas of land, and what the people do is they herd reindeer. And this reindeer herding is a part of their culture. And what they do is they present young reindeer to the children of various families. So this becomes their capital as it grows. And families have, thousands of reindeers who they really take care of them very well. They leave it out in the open in the summer months so that these reindeer go out, they feed themselves properly, they become nice and fat. And by the time the winter comes, they are brought back to their, places where they live in these laplands. And at that time, it is important to get them all back, because that's the only way they know how many reindeer they actually have. Also, they need to keep track of how many calves that the reindeer have, and in order to make sure that which reindeer belongs to whom, they etch something on their ears, as they punch holes in a certain pattern, so that they can recognize what herd belongs to whom. Now, in 1962, the snowmobile was imported from Canada. And that was thought of a fantastic innovation for them, because now they can go for their yearly, instead of them going for the yearly trading journey, which is about 200 miles away, which used to take days. They can now do it in, a much more lesser time. It used to take weeks, sorry. Now they can do it in much more lesser time, in days. Also, this whole procession of reindeers used to go to this particular place called the communal corral, which was a routine exercise, which was done by all the various families put together. It was a tradition, it was a cultural act, it was a ceremonial act, and there was reindeers, and they used to trade reindeers for its meat, for different things, to gain other suppliers at the various trading points that they used to go to. They used to go by skis, and there used to be also this herding that used to happen twice a year, because these reindeers have to be brought back together. With the advent of the snowmobile, and which was a very attractive proposition for them, because now the travel time has come down drastically. Now, there were new things that got introduced. One is that these snowmobiles were creating a lot of sound, which was scaring these reindeers away. And these reindeers would run away into the forest, and they would it would be a task to kind of get them back. And it would, the whole rounding up exercise, was not all that successful. They could not get the 100% reindeer. They used to get maybe about 2/3 of the reindeer only back. Secondly, what happened was, that because of this adoption of snowmobile, which was adopted by almost 85% of the families out there, they suddenly saw that the cost of herding started going up. It was much more costlier to do the roundups. It was much more costlier to ensure that the reindeers, to recognize whose reindeer was belonged to whom. There were unidentified calves. That was about 80% of the calves were not even identified who it belongs to. And suddenly the equitable economic structure of the families out there started to kind of dismantle, because those who could start affording the higher cost of reindeer herding survived, and those who could not started doing other things. They were selling their reindeer to the people who were able to buy, and the richer soon got richer, and those who could not do it, they were beginning to lose out. So it led to the people in these laplands to do other jobs, such as becoming snowmobile mechanics, such as becoming a part of the welfare system, and such as leaving that place to the cities. And these families, which were all united and together, they started all breaking up. Pretty much in 10 years, there was this whole disoriented society out there, and there were 3 rich families, and the rest were all disorganized. So what does this teach us? Okay, so this one is can be analyzed by 2 overall principles. One is that the first order principle is that the snowmobile coming out there was fantastic. It reduced the cost of production, it generated more profits, but for those who could afford it. And the initial embracing of this technology was fantastic. However, as we just saw, the second order was, it changed, was infrastructural in nature. It changed the nature of work. There were a number of different kind of other innovations that have happened, but it fundamentally changed the nature of the work, because people started doing other jobs like mechanics and like clerks in the cities and so on. Also, this helps us reflect in a couple of myths, that by having an infrastructural technology, it causes a revolution. Like the 4th industrial revolution, the way we construct it is all based on robotics, AI, and these new technologies that we imagine it to be changing the way we look at the evolution of the world out here. The second thing is the fallacy of technology determinism, which means that can we determine in which direction the technology is going to go and make a case for it. And that is the standard way, when we look at startups in the Silicon Valley, they would typically do, and we also do it, we evaluate all the startups in our network based on, what is the technology that they bring on the table, and in what way does this technology going to make a difference to us, and to us as a huge corporate, and to others who are our customers, etc. The broader picture is that people are actually making choices about the use of technology. And it is these policy making that makes a difference. If people are beginning to use technology, then it will find its space by the larger society, by policymakers, etc. In this process, ideas matter, and innovation will swarm if such a thing happens. From Finland, I would like to bring our context into the larger urban cities that we live in, and the larger environment of countries that we live in. This is a book called Digital Nation, written by Chandra, who is the chairman of Tata Sons. And the key argument here is about human capital, and what is the relation between them and these new technologies that are out there. Is it even possible to see this multi-order effects? That is the question I have. So imagining a 2030, and India is among the top 3 economies, and he argues that this reality is possible, that even with the new technologies, there will be new jobs that will be created. He also looks at painting a picture of what happens to these hundreds and millions of people who are otherwise doing very low skill jobs, can they be educated in a manner that they can do higher skill jobs? And the disruption and technology is the firm base out there. Now, I would like to break this up into two buckets. One is the labor demand, and the second is overall education. And this, how do we keep pace with these technological innovations when people need to constantly be reskilling and upskilling themselves? This calls for us to look at, how are we looking at labor demand? How are we looking at education? Because the future models of work are getting created as we are living it. Clearly, the bridge is there, but the bridge is not yet ready. And the bridge is for us to imagine, because in this imaginary of our constructs of how we are looking at the fourth industrial revolution, and in particular the 3D printed homes, it is important to see how are we going to look at these bridges, because there is going to be this new technology which is out there, which is going to be taken up by society, by different entrepreneurs, by industry. And if it does happen in a very massively scaled way, what is the cause of it? And which I was mentioning before, was because the society is embracing it. But then that would result in a new kind of a labor demand and a new kind of education, which is required in order to sustain a new revolution of this kind. Three specific stakeholders are the state or the country, the government, the industry, the market on the right-hand side, and the universities on the left-hand side. Now, change can happen because of incentives that the government is giving for performance by academia and performance to the industry. Academia, of course, would use that kind of funds for based budgeting, so that they are able to prioritize research in the specific areas, such as this 3D printing. And finally, the market decides, how are they going to use this particular new technology? And that is where it comes to this policy making. Academic institutions also want to ensure that how do they reduce the cost of education, and these are the kind of forces that are driving them to make decisions. How do they diversify revenues? How do they embrace new technology? How do they improve the stakeholder experience? How do they improve the operational experience? Similarly, industry is pretty much a learning engine. Employees who are there in the industries, like TCS, they are constantly being trained to ensure that they are able to utilize these new technologies and implement them. If we have a customer demand, very clearly we would be wanting to upskill and reskill our folks to be ready to embrace these new technologies. That's what we do constantly. The growth of people within an organization happens. And in particular here, I want to make a comment on the gig economy. 50% of the US economy in another 5 years is expected to be working in a gig economy mode, because not all people can work in organizations. Even TCS, for example, is an organization of 500,000 people plus. And we are also looking at new ways of how do we expand. And a co-innovation network is one such network, which is embracing the emerging technologies and all the innovation from outside in. There is internal training that keeps happening all the time. There is, training programs such as master's program that we have got called contextual masters, and many, many training programs. Also, our folks are allowed to do any training program, both within TCS as well as outside, that is available within universities or with other platforms such as Coursera, LinkedIn, etc., etc. So there is learning happening everywhere. There is, if you want to break up how this learning is happening, it is basically a collage of skills. Now, this collage of skills, which I have put in here, because everybody thinks about skills in their own specific way. There is the human capital theory, which I call it as HCT here, which basically means that the responsibility of developing skills belong to an individual. It's an individual decision in this neoliberal capital world that we live in. And we make our own decisions, and these decisions can be good. I mean, these investments in our education may not be good. It all depends what decisions are made. And this has been a theory which has been utilized for the purpose of modeling a lot. Then there is another method of looking at skills, which is the personal qualities, and it's called the Pes formula. And here it is more of trying to say that, this is productivity which is involved. There is, expansion of skills that is involved. And there is also the choice of, what skills one want to acquire that is involved. It's at a personal level also, besides, just at the market level. There's another author, Crick, who looks at this whole dimension between personally how a person is motivated versus, what they would decide from a market perspective. Then there is the futures of work. Let's say another example is Buchanan, who is talking about the fact that just education is not the answer to all the challenges out there in the future of how work would be like. And therefore, he brings back the focus on the institution, that the education institution does their own thing and the industry can do their own thing, whether it is also skills that are required for employability. It is probably in the interest of the industry to create those kind of skills. The argument here is that there is so much of skill-based theory that exists out there. And while we focus on these policies of what skills one would like to acquire and what are the policies to frame for that, both from industry perspective, the government perspective, and the academia perspective, in order to ensure that there is congruence with the technology evolution that is happening, my question is, we should also be aware of what skills are machines learning that we are programming, which is the AI part of the fourth industrial revolution. What is it that we are training these engines, which maybe are our partners in this whole process of getting into this new race? And this is a kind of a theoretical framework which I've created, which I wanted to share. So there are the policy producers variables, okay, which are the policy producers are industry, academia, and the government, and the consumers variables, which are, let us say, the startups at large, let us say the learners at large, who really want to learn out there, acquiring these new technologies. It is not just meant for the people who are at the elite part of the value chain, but also the basic workers, the construction workers as well. Any policy by, let's say, theory creates new winners and losers, any policy change. So there is the issue of access to, whether it is jobs and access to education, and there is this issue of inequality that happens all the time. So if we look at technology innovation as a process that is institutional, which is cultural and political, combining all these as an innovation process, and then we look at policy entrepreneurship as a lens to ensure that co-innovation and collaboration happens by design. So I would like to start concluding. So what are the key factors that should be considered from a technology perspective? Now, we believe that when we combine different kind of technologies, it starts delivering exponential value. We call it in TCS the digital exponentials. And an example is like the mobile phone, because of what it does with Web 2.0, and now the new Web 3.0 is under construct. It gives a certain kind of connectivity which gives power to individuals. Similarly, now if you look at 3D printing homes, along with other associated technologies, that would create some kind of an exponential change. I have listed three here. One is, I think, blockchain, which is about the auditable carbon footprint. The second is the material innovation, about which some of the speakers have talked earlier this morning. Third is metaverse itself, the virtual reality, the Web 3.0, where we are going to be having immersive experiences in our own homes and on own workplaces. Now, what kind of a social, technological, political, cultural change will this bring in? will this, for example, because we are looking at the fourth industrial revolution imaginary, ensure that even at the remotest places on Earth, including Finland, including northern parts of Canada, can we have more advanced homes? And can we look at these homes being built in a much more sustainable way? Can therefore people be at their homes and be connected to the rest of the world, which is anyway possible now? And will this change the kind of migration from rural to cities, and would it enable reverse migration? These are some of the questions here. From an economic, social and educational point of view, there is this convergence of this metaverse, and which is what I was just talking about. And would that make a change in home prices? Would that will that create any change in the supply chain and the stakeholders if this particular technology in 3D printing becomes mainstream? The third aspect is what happens to the construction workers who are at large working, and how do we look at how do they become a part of this new system? How will they be getting trained? Who will bear the cost of training? And what are the kind of education models that will be required out here? And I was just kind of referring to the new micro credentials, which are industry aligned skill-based courses which are coming up. How will these courses be designed? And the final part is, what about the caring jobs? These are all the kind of jobs which are much more real, materialistic, etc. The caring jobs are the ones which require care, which is like, let's say, nursing, let's say, to some extent, even doctors or people who take care of animals, etc., etc. So with that, those questions, I would like to conclude by saying this, that designing technology futures involves determining stakeholders and identifying co-innovation factors in policy making, which was the point I was trying to make in this presentation. Thank you so much.
This was a very, very interesting workshop. So clearly, we're looking at a new technology. We're looking at its potential. We're looking at the world that has gone around the world. We're looking at the needs. We're looking at the time scale. We're peering into the future to see exactly where this would go, comparing it to existing technology, looking at where the drivers are. I think there's a lot of questions here, obviously. But clearly, to me, it's the right step. And I think this industry, government, academia collaboration that we see today here is absolutely the right mix, I would say, for generating solutions that we do want at the end. So it's been, and of course, we had some wonderful speakers here that stayed up until wee hours of the morning. I was feeling bad for Yame. I think it was like 4 in the morning there, actually. But she was still very alert. I was very impressed by that. But, it was wonderful to see the international cooperation here. Wonderful to see everything come together. So I hope you enjoyed the day. And as from IC Impacts, which was one of the organizers of the event, this means a lot because in the Canada-India corridor, I think what we're looking at basically areas where we can collaborate, and it seems like these kinds of technologies are absolutely the right ones to bring, through a collaboration into the community. So I think we're very excited about that. The other partner, of course, we have is our Consulate General here. Thank you so much, sir, for your time today. Really appreciate that, and of course, Najesh Ji and everybody else that sort of helped us, set this up, helped us coordinate this. It's wonderful to see this collaboration flourish, and we certainly will have a lot more productivity going forward as a result of this. So thank you all for coming. Thanks also to the Student Engagement Committee. I'm sure you will get the last word as well. So thank you to the Student Engagement Committee as well that put this program together. And last but not least, I'd like to thank Feria. Feria, again, thank you so much for everything. Thank you again for taking care of so many other things. And thanks to our IC Impact students who are here as well. Thank you so much. And to my group, Sierra, certainly always rise to the occasion and help us. CIRA is my research group, which is the working on infrastructures, sustainable infrastructure group. So that concludes the program. Thank you again for coming, and I hope you will stay for the networking reception. Thank you.